Welcome to Electrical Engineering with Excel. In this video, we will look at specifications that come to us in the form of a graph. Instead of using a ruler on paper to get the desired answer, we will use a free web-based plot digitizer and turn the graph into an equation utilizing Excel's Trendline tool. Often, the plots in device specifications, just by their nature, will be related to a mathematical function, like this one that appears to be parabolic. We will use a web-based tool to digitize the plot and produce XY data pairs. Those are brought into Excel and a scattergram is created. A trend line will be added. The equation for the trend line is displayed on the chart. Excel has numerous trend line options. In this case, a polynomial is the appropriate trend line. We can get the answer we desire from the plot using an equation rather than using graphical techniques. The first example is a heatsink from CIU devices. This series is made for heat-sinking TO220 style packages. It has various part numbers cut to various lengths. How do we determine the thermal resistance for a specific heatsink? Here's the specification plot for that heatsink. The y-axis is the temperature rise above ambient, and the x-axis is the dissipated power. The plot in red is the characteristic without airflow or forced air. It's clear to see right away the plot is nonlinear. How do we determine the thermal resistance of this heatsink at a specific dissipation? We get out a ruler and draw a vertical line at 6 watts on the horizontal axis, then draw a horizontal line at the intersection of the plot. By visual inspection, that looks like about a 62-degree rise at 6 watts. We divide 62 by 6 and get 10.33 degrees C per watt. Simple enough. This is fine for a one-time result, but imagine a design where the dissipation changes from one design iteration to the next, or imagine the same heatsink part number being used in multiple designs. There are many plot digitizers available, but I found this free web-based digitizer by Automeris. This is a link to it, and you will find the link in the description below. Here's a demo on how to use it. From the File menu, select Load Image. You can browse for it, but I'm going to drag and drop it. The default plot type is a 2D XY plot, so click on Align Axes. Next, we will click 4 known points on the axes in the order shown. Starting with the left of the x-axis, you can use the arrow button to nudge it into place while looking in the magnifying window in the top right of the screen, and then proceeding on with the other axis points. To complete the calibration, you must enter the axis values. X goes from 0 to 10, and Y goes from 0 to 100. Now to do the extraction, click on the foreground color and select the color picker and click on the plot color, in this case the red plot. Now for a mask, select Box and drag a box around the plot. Beware the legend has red in it too, and it will get digitized as well. It's okay if it did, as any data points can be deleted. Then select Filter Colors, and you can see it has picked up the lower plot as well. Reduce the color distance to 20 and click Filter Colors again. Now the plot we want is clearly detected. Press Run, and you can see there are points all digitized across the red plot line. Now click on View Data. Now the XY values are shown. Select Copy to Clipboard. Now open Excel and paste in the values. Notice they come in as text. From the Data menu, select Text to Columns. Delimited is selected by default, so click Next, and then check the comma box to add it as a delimiter, and click Finish. Select the data and insert a scattergram chart. Select the data series and click the right mouse button to format the data series and set the line width to 0 so we can see the upcoming trend line better. Then right-click on the data series again and select Add Trend Line. Select Polynomial. It defaults to second order. Check the display equation on chart and R² value. Increasing the order to 3 makes for an R² value go to 1. And there we have the equation for the curve nicely fit. This was so easily done. Here's a summary table of the coefficients for the various heatsink part numbers. It calculates the temperature rise for a given power dissipation input. The cool thing about polynomial formulas in Excel is there are no parentheses required. The natural precedence of operation takes over. With the temp rise calculated, the sink to ambient thermal resistance can then be made available to do your thermal analysis. In the case of forced air cooling at 200 linear feet per minute, it's obvious the temperature rise versus dissipation is linear. Drawing a horizontal line across the intersection at 10 watts gives us 54 degrees. Therefore, the thermal resistance is 5.4 degrees C per watt. Moving on to a different example, the LM117 internal voltage reference is temperature compensated. It's quite clear to see this is a parabolic or second-order polynomial shape. Digitizing a plot like this is more difficult since the grid lines are the same color as the plot and nearly the same width. It's further complicated because the critical part of the plot is the turning point at 25 degrees, which lays over the grid line. The plot digitizer we are using does perform grid removal. I tried with marginal results. It worked best for me to use the pen mode to make the mask for extraction. I'll skip over the grid calibration steps like in the previous example since you have already seen that. First, pick the foreground color of the plot, which is black. Then select Pen to make the mask. The default width seems to work good in this example. You simply color over the plot line. If you miss a spot, you can go back and catch it. You can also erase any overshoot that you may have had. Then click Run. You will see a lot of extraneous points where the mask was over the grid lines. It's pretty easy to go delete those. Click Delete Point and select the dots to delete. Then select Adjust Point and click on any that need a tweak, using the arrow keys to adjust. Then click View Data and copy the points to the clipboard. Then paste into Excel and create a scattergram chart. Right-click on the series and select Add Trend Line. A second-order polynomial fits great. All you need to take from these sheets are the polynomial coefficients to use in your design spreadsheets. This simple equation in Excel returns the reference voltage versus temperature. Thanks for watching. Please click the like, subscribe, and notification bell so you don't miss any upcoming content.